Let's understand the deformation of the continuum. For that, let's go back a bit and think about how actually photons are emitted. You know that any charge that is accelerated is going to emit a photon. In German, that's called Bremsstrahlung, which means breaking radiation. As derived from electromagnetism, a charge under acceleration will radiate. So let's consider a very simple system. You have a proton and an electron. Consider the reference frame of the proton, so the proton is now moving. As the electron passes, it will be deflected by the proton's electric field, as you see here in this figure, right? The electron approaches with an impact parameter. It's going to be deflected by the electric field of the proton. And then in this acceleration, the electron loses energy and emits a photon. So let's calculate what is the emissivity. We want to show that if you have a situation where this emission becomes optically thick, it's going to become the Planck function. So we want to know here the emissivity of Bremsstrahlung. So let's look back at intensity and emission. We wrote the emissivity law, which is that the intensity is the emissivity times the density times the path. We can write this in terms of energy. If we write the definition of intensity, that the intensity by definition is the energy over the area over frequency over solid angle over time. So if we isolate the energy and now substitute the definition of the emissivity, and ds dA is the volume. Well, from this, you see that the unit of emissivity, if you isolate the emissivity in this equation, is erg per second per gram per steradian per hertz. So we see here that emissivity essentially means power per mass. That's power, and this is mass. It's actually power per mass in a direction per frequency. But essentially, it's power per mass. It's measuring how much energy per time a gram of material contributes in a particular wavelength and direction. Now, if you multiply that by the density, you eliminate the dependency on the mass. And now it becomes the power per volume. This is the power and this is the volume. So now it's measuring how much energy per time every cubic centimeter of material contributes in a particular wavelength and direction. So let's use these definitions here to find out what is the emissivity of Bremsstrahlung. So what we want to know here is J rho. Isolate J rho here, and then what you have is the energy over volume per frequency per solid angle per time. Isolate J rho here, and then what you have is the power, dA dt, dE dt, per volume, per frequency, per direction. So let's focus at this quantity here, the power per frequency. Also known as the spectral power. What we need here is a frequency and a power. We can approximate this, the derivative of the power over the frequency. We can do a crude approximation as the power over the frequency. So the question becomes here, given the proton and the electron system emitting a photon, what is the power and what is the frequency? For the frequency, we can assume that the electron is going with the velocity u, and it has an impact parameter b from the proton. So the interaction time is b over u. And from that, you can construct a characteristic frequency. It's 1 over time, which is equal to u over b. As for the power is going to be given by Larmor's formula, which gives you the radiated power of a charge undergoing acceleration. Larmor's formula states that the power is twice the square of the charge times the square of the acceleration over 3 times the cube of the speed of light. The acceleration is given by Coulomb's law. It's the product of the charges over the square of the distance divided by the mass here, where me is the mass of the electron. So if you plug in this acceleration back in the power, so you have the power and you have the frequency. So you have then the spectral power, or at least a crude approximation for the spectral power. Now, this is for an isolated system. This is for an isolated electron radiating. If you want to pass from that to an ensemble of particles, you have to consider that the impact parameter is given by the average separation of the protons. Given that the number density of protons is n, we can construct a typical length from this, which is the typical separation between the protons. which is equal to 1 over the cubic root of the number density. And that gives the impact parameter. That's the typical distance between two protons. If you substitute this impact parameter into the spectral power, okay, so now this is the power for one single electron in an ensemble of protons. If you want to convert that to emissivity, then you have to recall the definition again of the emissivity in terms of the spectral power. So what we're missing here are the factors of volume and solid angle. For the volume, we multiply by the volume density of the emitters, which are the electrons. So let's give a subscript here, P, for the number density of the protons. So have that the spectral power, the dPdE, is equal to J rho, and then the infinitesimals of volume and direction. Well, we integrate this to have a volume average and a directional average emissivity. So if we take the integral in volume, what we have is the inverse of the number density. Now the number density of the emitters, which are the electrons, and the integral in direction is 4 pi. So this is going to give us a factor 4 pi over number density of electrons multiplied by this average J rho. So if we substitute this, the expression that we found for the spectral power, then we find what the J rho is. So this is an expression for the ensemble emissivity. Now, notice that this still depends on the velocity. Now, in an ensemble, particles will have different velocities, so this equation cannot be the whole story. To get to the emissivity of the ensemble, we need to integrate over the velocity distribution. If we are in thermodynamical equilibrium, then the number density of particles with velocity between u and du is going to be given by the Maxwell-Boltzmann distribution. And the Maxwell-Boltzmann distribution is, so an electron with velocity 0 should contribute an infinite emissivity according to this equation. But as you can see from the Maxwell-Boltzmann, the number of such electrons is going to be very, very low, so the emission will be finite. You're going to be multiplying infinite by 0. The reason why an electron of 0 velocity would have an infinite emissivity is because the interaction time is very long. Remember that the interaction time was the impact parameter over the velocity. A very slow electron is going to spend a lot of time interacting with the proton, being accelerated and therefore emitting. But it's only a very, very small number of electrons that have this very small velocity. So the emission in the end is going to be finite. But this shows that if you want to find the total emissivity, you need to weight the emissivity of a single velocity ensemble of electrons by the Maxwell-Boltzmann distribution of velocities. So let's do this weighted average. Call J rho chi, and then the average, let's call it the thermal average. The thermal emissivity is going to be the emissivity with a single velocity weighted by the Maxwell-Boltzmann distribution. Now doing the appropriate substitutions and solving the integrals. Now this is an interesting result. We say that the emissivity does not depend on the frequency. It is completely flat. The electrons are accelerated in the electric field of protons. As electrons are accelerated in the electric field of protons, they emit photons of all frequencies and at the same rate. The Bremsstrahlung emission depends only on the number density of the emitters, the electrons, the number density of the protons, and the temperature. Now, in light of quantum physics, this result cannot be correct, because we know that the photon energy is proportional to the frequency. If you throw in here that the energy is proportional to the frequency, and you have the electrons are emitting at all frequencies, that means that you can have an electron of infinite frequency, which would mean infinite energy, and that is preposterous. This result cannot be correct. Indeed, there is nothing quantum in the analysis that we did, but we can do a semi-classical correction to this by realizing that the electron cannot radiate a photon of energy higher than its kinetic energy. And indeed, this is going to lead to an exponential cutoff in the emission. That's the thermal cutoff. We can include in here an exponential cutoff, this thermal cutoff is the exponential minus h nu over kT. That means when the energy of the electron is comparable to its thermokinetic energy. So that's how the Bremsstrahlung spectrum is going to look in the end. You have a flat profile, and then an exponential cutoff in here, which is at the frequency corresponding to the kinetic energy of the electron. Now, Bremsstrahlung occurs in astrophysics whenever there is a very diffuse and hot gas. So you can expect it when you have ionized gas. Bremsstrahlung is typical in X-ray emission from cluster of galaxies. You have here the optical image of a galaxy cluster. And then here, then, when you look in X-rays, you have this diffuse emission. This diffuse emission is Bremsstrahlung. It's characteristic of very optically thin emission in ionized gas.